So here let's solve the exercise. I strongly suggest you don't watch this video. You try the exercise first and you have an achievement when you find the solution. And then you can just check it against the answer that is given in a very discrete way in the lecture notes. So how do we address this exercise? Well, we want to find first the cumulative distribution function of x, which is, well, this will be the probability that x is less than t. What is x? This is e to the u, so this is the probability that e to u is less than t, and which is the same as e to the u is always a positive non-negative number or a positive number. So we can already say this is 0 when t is negative. When t, this is 0 when t is even less than 1. Okay? When t is less than 1, then how can an exponential be less than 1? Well, we need u to be non-positive, and this has probability 0. And well, when t is larger than e, then we're asking, is e to the u less than e to the t, or less than some t e? Well, this probability is 1. Okay? It is 1 because, well, because this is the probability that u is less than 1. So this will be 1. And then what became interesting is when exactly t is between 1 and e. Then what is it? Well, then now t is between 1 and e, so we can continue developing from the previous expression. This will give us what? This will give, we can take the logarithm because t is now in a very safe region. So this will be the probability that u is less than the logarithm of t. And well, we know what is the uniform random variable looks like. Log t will be a number that will be between 0 and 1, because t is between 1 and e. So when we take logarithm, it's between 0 and 1. And we know the probability that the uniform variable is less than a number, and that when that number is between 0 and 1, it is the number itself. So this is equal to log t. So we found the cumulative distribution function of this function x. We found it to be log t. Okay, I know maybe you already know an easier way to do this, but here we are practicing the concept. We're practicing how these tools play together, so let's stick to this otherwise inefficient way of solving it. So ft is log t, so what would be the candidate f x of t? It should be the derivative. Well, here we have log t. Okay, but only between 1 and e, so f of x would be the derivative, we know it's the derivative of the logarithm, 1 over t, times the indicator from 1 to e of t. So we found the density. It is 0 outside this interval. It is 0 outside this interval. And how can we check that capital F is the integral? Well, just look, what is the integral from minus infinity to x, or from minus infinity to t? of fx of x dx. Well, we can separate this into first the integral from minus infinity to 1, and that part will be 0. And we can take t larger than 1, otherwise the integral is 0 also. And we can also take t less than e, otherwise this integral will be 1. So when we compute the integral, what is the integral of 1 over t? And that will be the integral from the integral of 1 over t from 1 to x dt. This will be exactly e to the x. So this will be log x. And this is consistent with what we had. What we had where exactly? Well, this is consistent. This is our function f. So if we go back here to what we said before in the previous part of this video lecture, is we compute the derivative. We compute the derivative and check whether this holds. And this is what we just did. We computed the derivative, so let's navigate here. We computed what the cumulative distribution function of the variable x would be. Then we took the derivative of this function. We found what should be the density of this related to this cumulative distribution function. And to check that this is indeed the density, what we do is we integrate. We integrate from minus infinity until t, the function, and then we see what it gives. Or here at some point we inverted the variables, didn't we? So let's integrate until x, and use t as the random variable. And this is just a bad notation to indicate the Lebesgue measure with the variable t to be integrated. Okay, so this way, let's continue. Following this path, we found what the cumulative distribution function is. We found it on these different parts to be something different. And then we take the derivative, and we found the derivative to be 1 over t times this indicator. Well, in fact, it is 0 outside this interval. It is 1 over t inside this interval. And when t equals 1 or e, there is no derivative. So this function here, it has no derivative when you change from one line to the other. When t is below 1 and then it reaches 1. So these two expressions that we have here, they are in disagreement. These two expressions here, when t is less than 1 and suddenly it becomes 1. This function is continuous indeed, because if t approaches 1 from above or from below, we get the same value here of 0, but it's not differentiable. Yeah, it looks very much like this. This is not differentiable. And then here it's not differentiable again. So it looks like this, and this is just a piece of the logarithm.